Hi, and welcome to this next lecture on data structures and algorithms. Starting today, we will discuss some algorithms to find roots of equations. So, we are looking at the equation of the form fx equal to 0. What we will discuss today is a method called the bisection method to find the roots of such an equation, that is solutions to fx equal to 0. Now, we are typically interested in a nonlinear equation. For the linear equation fx equal to 0, the solution should be very straightforward. Basically, you are looking for the x coordinate corresponding to the y intercept of 0. So, it is very trivial. For linear equations, it is nothing but the intercept on x axis. Pictorially, this is what we mean. If this were your equation fx equal to 0, this intercept x dash would correspond to fx dash equal to 0. However, what do you do when you have nonlinear equations? And here is a depiction for a nonlinear equation. The binary search method basically is an iterative method. Instead of a one shot solution, such as in the case of the x intercept, you start with some 2 points, let us say point here and point here, and we will canonically call these points a and b. So, given a function fx, we will assume that it is continuous on this interval a b. Let us say the initial guesses are a and b. We will also assume that the function actually has at least one root between a and b. So, we might initialize a and b to be sufficiently far apart to ensure that the function does have a root between a and b. And of course, a sufficient condition for such a continuous function to have a root between a and b is that they have opposite signs. So, sufficient condition is that the sign of f at a is minus of the sign of f at b. Well, this basically means that the product of fa and fb is negative. Now, this is a sufficient condition, not a necessary condition. So, it is possible that fa into fb is positive and it still has a root, and classic case for us is going to be the squared function or x raised to an even power. So, consider function like this. This could be f x raised to 4. So, this indeed has a root at x equal to 0. However, fa into fb is always going to be positive no matter what your choice of a and b is. So, therefore, this is not a necessary condition, it is only a sufficient condition, and unfortunately binary search method operates under this condition. Finally, it guarantees finding only one root. So, it is possible that a function such as this let us consider this function. Now, it is possible that your initial choice of a and b are such that they cover two roots, but only one root is guaranteed to be found using the bisection method, and we will see why. By virtue of its reduction of the search space by half, it will either omit this root, the root on the left, or the root on the right. Only one of them will be found. An example of such a curve is a sine curve. So you have sine, also look at the cosine functions. So here is the algorithm for bisection method. You begin with points A and B such that fa into fb is less than 0. Now all these such algorithms operate on certain tolerance parameters. In fact, here we have two tolerance parameters. One is the tolerance limit on the function itself, so which means that you will stop when f of c is less than tolerance value. But there is also another implicit tolerance parameter, which is number of iterations. This is tolerance based on argument. So for example, you might have a curve which gets to 0 very gradually. So let us consider the following curve. Now a curve like this gets to 0 very gradually, and it is possible that even after lots of iterations you are hovering around 0 but not exactly 0. So until you have this maximum number of iterations and the tolerance is reached, you do the following. You basically set the upper and lower limit for further division. So imagine that A and B were the original probe points. We look at the midpoint, and let us say our midpoint was somewhere here, C was here. You then check if A into C is negative, A and Fa and Fc have opposite signs. If yes, then you know that a new search space can be here. So this becomes your new search space. And how do you do that? You do that by pushing B to C. That is what we have done here. On the other hand, it is possible that C is on the other side. So in that event, if C were on this side, you would set A to C, you would push A to C and search for the interval CB. So you have to keep track of the iteration number and then further look at the midpoint of the new interval. Please note that the algorithm stops or terminates when both these conditions are satisfied. So by design, it is guaranteed to run for the n max number of iterations. This method is guaranteed to converge by design because of both the tolerance parameters and because there is an increment in every iteration. Further, your search interval is halved for every iteration, which means there is a size of the interval after k iterations, assuming unit initial interval will be 1 upon 2 raised to k. So as you can see, there is an exponential decay or exponential shrinkage in the interval size. Despite all this, the convergence is slow. The question is therefore, can we be wiser in our splitting of interval? Could we do better than half? And is it necessary that you need to go on for n max number of iterations? Is it possible that you stop earlier? Is it possible that the algorithm becomes adaptive? Can the shrinkage be adaptive as you get closer to convergence? So we leave certain questions. Question 1, can we reduce interval for search by factor less than half? Can we adapt shrinkage and so on? In fact, if the initial guess is closer to the root, it will take more iterations to converge, primarily because the shrinkage is relative. So we would like to detect if we are closer enough to the root. And most importantly, this algorithm has severe limitations in what it can deal with. So reminding ourselves of one function for which we said the algorithm won't function is the quadratic function fx equals x square, or you could even consider x raised to 4. Now there is no way you can find a and b with opposite signs for the function. On the other hand, we know that there is a root, and we know that if you were to find a and b and be able to half the interval, you would actually find diminishing values of the function. How do you do that? Also, this won't work if the root is at infinity. So 1 upon x is a classic example. So here is the equation fx equal x square, which cannot be solved using this method. The equation fx is equal to 1 upon x has no root, but it is interesting that it just changed sign. So just because you change the sign as you go from, say, a potential point A here to potential point B here, you are going to actually search for a midpoint, shrink your interval, but you realize that unless you move away from the interval AB, you won't get to the root. So it's a fundamental problem with the assumption that if A and B have their signs changed, the function changes signs between A and B, then the root will be between A and B. But recall, our assumption was subject to the assumption that f is continuous between A and B. So note that f was to be continuous in the interval, closed interval AB, which is not the case here. So only under this condition was the change of sign a sufficient condition. So what do you do if these conditions don't hold? More about this in the following lecture. Thank you.